Hello students, welcome back. It is second part of the real number where I have said it contains 6 marks, the fundamental theorem of arithmetic. This one we will cover in this video fully. In your earlier classes, you have seen that any natural number can be written as a product of its prime factors. Here it is written any natural number. So one small error is here. Any natural number it should not be, because when you say any natural number then 1 should also come here, right? But 1 is not a prime number, so 1 you can't write in the form of prime factors. Okay, so it should say every composite number that we are going to see how it will change from this to that. So NCERT is starting from the basic, from assuming that any natural number can be written as a product of its prime factor. So it is not justifying this statement, it is saying like you have studied in your earlier classes that any natural number can be written as the factor of its prime numbers, means as a product of its prime factors. So for instance, it is giving some example like 2 can be written as 2, 4 can be written as 2 into 2. Both 2 is a prime number, right? What is the meaning of prime number? Which will not have more than 2 factors. One is itself and one is 1. That's it. So 253 can be written as 11 into 23, means 11 is also prime, 23 is also prime. Like this we can write any number, any natural number in the form of, in the product of prime numbers. Now let us try and look at natural numbers from the other direction. Means other direction means what? Can we write natural number by multiplying prime numbers? For example, can we write, take any prime numbers in your mind. Suppose 7 and 2. 7 to 14. So yes, we can write the prime numbers first, and then from that, multiplying that prime number, we will get some natural number. Take any collection of prime numbers, say 2, 3, 7, 11 and 23. If we multiply sum of all of these numbers, allowing them to repeat as many times, means there is no restrictions of using the number many times if you want. So if you are multiplying it in different way, different permutation combination you are using here, so different numbers it will generate. So in this way, some examples are given here. You can see it carefully. It is arranged in different way. Okay. But in all this is taken care that it has the smaller number first and then the larger number, like it is in ascending order. So it is written in order. Now let us suppose your collection of prime include all the possible primes. Okay, all the possible primes you have in your collection. So do you think that primes have the size? Means do prime number have limitation? Does it contain only a finite number of integers or infinitely many? Obviously it will be infinitely many. Okay, so in fact there are infinite many primes. So if we combine all these primes in all possible way, we will get an infinite collections of numbers, because prime numbers have no limitation. There is no end of prime numbers. All the prime and all possible product of primes. The question is, can we produce all the composite number this way? What do you think? Do you think that there can be a composite number which is not a product of power of primes? So no, obviously no. Whenever question mark is there you have to stop for some time and think on it. So can we produce any composite number which will not the product of prime numbers? No. All the composite number can be written in the form of prime numbers, in the product of prime numbers. Before we answer this, let us factorize positive integer, that is do the opposite of what we have done so far. We are going to use the factor tree with which you all are familiar. Here also they are assuming that you are familiar with factor tree and hope you have studied about it. Let us take some large number, say 32,760, and factorize it as shown. So here you see it is factor tree 32,760, it goes into table 16,380 times, then it goes into table 8,190 times. Like this it is written all the factors of this number. So you can see on the LHS side all these are prime number, 2, 2, 2, 3, 3, 5, 7, 13. These all are prime numbers. Now see in the next page. So we have factorized 32,760 as 2 power 3, which can be written as 2 raised to the power 3, 3 raised to the power 2, 5 into 7 into 13. So they have written in the product of powers of primes. Let us try another number, say 1, 2, 3, 4, 5, 6, 7, 8, 9. This can be written as 3 power 2 into 3803 into 3607. And they are saying, of course, you have to check that 3803 and 3607 are primes or not. So you can try it with several numbers, and how you will check whether it is prime or not? Divide with some numbers like 2, 3, 2 divisibility rule, 3, if it is not divisible by 2, it will not be divisible by 4, like that you have to check. So 3803 and 3607 is a prime number. Conjecture means till now what we have studied. From this we can conclude it that one unproven fact we got, that every composite number can be written as the product of powers of primes. Okay, till now means it is not saying in reality, it is saying up in this, when you are listening to me and you are reading NCERT, till now we reached up to here. In fact, now it is giving the fact this statement is true. So it is not unproven, it is proven, it is true, and is called the fundamental theorem of arithmetic. This is only the fundamental theorem of arithmetic because of its basic crucial importance to the study of integer. Let us now formally state this theorem. So now they are going to say you the theorem, and it is theorem 1.1 of this chapter. Fundamental theorem of arithmetic say every composite number. Now what I said you initially only, that natural number is not the correct word. So they will say every composite number, and the smallest composite number starts from where? 4. So every composite number can be expressed, factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Okay, so we will do fine tuning in this also, but you have to remember composite number can be expressed, factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. And one more thing you can see, sometimes they will mention some mathematician names, some unique datas, okay, some different data like this informations. So you have to just go through it, because from exam perspective I don't think it is important, but as we are going line by line, so we will see this also. An equivalent version of theorem 1.2 was probably first recorded as proposition 14 of book 9 in Euclid's Elements. Euclid's has this book 9 is given, no, like this book 13 up to book 13 is there, and his each proposition is like mind blowing. If you will read those, no, you will start loving maths. Each one has written with lots of focus, lots of understanding. I don't know what kind of person he was. Maybe he was thinking too much on maths or numbers. He has given lots of interesting theorems, lots of interesting facts. Okay, so you can go through it. Now it is said that earlier it was in that book where it was Fundamental Theorem of Arithmetic. Okay, however, the first correct proof was given by Carl Ferrandis Gauss, whose image is given here. He was from 1777 to 1855, and in his book, that in his thesis or a hypothesis maybe, it was Disquisitiones Arithmeticae. So Carl Ferrandis Gauss is often referred to as the prince of mathematicians. He is called prince of mathematician, can you understand, and is considered one of the 3 greatest mathematicians of all time, along with Archimedes and Newton. Hope you all know the name of these 2 scientists. Mostly we know them for physics theorems, physics research. He has made fundamental contribution in both mathematics and science. He also made fundamental contribution in maths and science. Now coming back to our fundamental theorem of arithmetic, says that every composite number can be factorized as a product of primes. Actually it says more. It says that given any composite number, it can be factorized as a product of prime numbers in a unique way. In unique they did black bold. Why? Because it is important word. Except for the order in which the primes occurs. That is, given any composite number, there is one and only one way to write it as a product of prime. See how many times they are forcing on this unique. So sure one question will come from here. As long as we are not particular about the order in which the prime occurs. So for example, we regard 2, 3, 5, 7 as the same as 3, 5, 7, 2, or any other possible order in which these primes are written. This fact is also stated in the following form: the prime factorization of a natural number is unique except for the order of its factor. Okay, like this also we can write. Now for order also we will do the solution in this part. See how beautifully we will solve that problem also here. In general, given a composite number x, okay, any composite number, we factorize it as x is equal to p1, p2, p3, like just now which we did for prime number 32760 32,760. We have written it in the form of 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13, right? So that prime numbers, different prime numbers are denoted here p1, p2, like that, where p1, p2, p3 are primes and written in ascending order. So to write in ascending order, we can arrange it in this form. So p1 has to be equal or lesser than p2. So p2 can be greater, p3 can be more greater than that or equal to p2. So like that, if you will write this statement, if we combine the same primes, we will get powers of primes. For example, 32760 can be written as 2 into 2 into 3 into 3 into 5 into 7 into 13. So if you will combine same primes, like 2 power, you can write 2 power 3, 3 power 2, 5 into 7 into 13. So once we have decided that the order will be ascending, then the way the number is factorized is unique. Now we can say it is unique without mentioning that line. If you will mention it like p1 has to be lesser than or equal to p2 and p2 has to be lesser than or equal to p3, like that. So the fundamental theorem of arithmetic has many application both within mathematics and in other fields also. So in next video we are going to see some of the examples how we are going to use fundamental theorem of arithmetic. Quickly we will recap it, what we have studied. It is very interesting. We have seen that fundamental theorem of arithmetic works for composite number, not from natural number, because one is a natural number but it is not a composite number, not a prime number. Okay, then we have seen that any number can be written in the form of product of prime numbers in a unique way, and we don't see order. So here we have seen that prime numbers are infinite, many prime numbers are there, so composite number will also become infinite. So every composite number will have their unique prime factorization. Okay, and then we have seen how to write it in a way where we have to arrange it in a ascending order. Then we have covered theorem 1.1, where it clearly says every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occurs. Then we have seen little bit about this mathematicians and scientists. Then we gone through the prime factorization of a natural number is unique except for the order of its factor. Prime factorization of a natural number, again here they are using natural number, so I said you it should use composite number. So we will go with the theorem statement, theorem lines. Okay, in theorem it is written clearly that every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occurs. Okay, so how to arrange it, that is also clearly mentioned here, like p1 has to be lesser than or equal to p2. So these things we have seen. So we have covered fundamental theorem of arithmetic. In next video we will see the application of it. Thank you student. Bye.